Have you ever wondered what the universe was like, just a split second after it was born? What if I told you that we can actually recreate those first fiery moments right here on Earth? Yeah, it sounds like science fiction, but it's really happening. So let's dive in, because we are about to explore one of the most incredible scientific instruments ever built, the massive detectors at CERN. Deep, deep underground, right on the Swiss-French border, scientists are doing exactly that. Down in a cavern 100 meters below the surface, they use the Large Hadron Collider to whip particles up to nearly the speed of light and then smash them together. What you get are these tiny, unbelievably hot fireballs that are basically a perfect snapshot of our universe just after the Big Bang. And that's the whole point of this, to get a look at this primordial soup, this quark-gluon plasma. It's a state where the building blocks of everything, the quarks and the gluons that glue them together, were just floating free. If we can understand how that cooled down to become the universe we know, then we're basically reading the original instruction manual for reality itself. So to see these mini Big Bangs, you can't just use any old camera. You need an instrument on a scale that is just mind-blowing. Let's focus on one of them, the compact muon solenoid, or CMS. And trust me, it is an absolute beast of a machine.
First off, let's just talk about its weight. The CMS detector weighs 14,000 tons. To put that in perspective, that's heavier than the Eiffel Tower. It's this colossal, monumental piece of engineering, all designed to see the tiniest, most fundamental things in existence. The contrast is just amazing.
And it's 21 meters long. So you might be wondering about that word, compact. Yeah, that's kind of the physicist's little inside joke. But seriously, for a machine packed with this much technology and material, it is an incredibly dense and brilliantly efficient design.
At the very heart of this machine is its magnet. And this isn't just any magnet. It's the most powerful solenoid ever built. We're talking about a magnetic field that is 100,000 times stronger than the Earth's. It's not even a close comparison. This incredible force is the key, because it's what bends the paths of the particles flying out from the collision, which is how scientists can figure out what they are.
Okay, so this brings up a pretty big question, right? How in the world do you build a 14,000-ton, ultra-high-precision machine in a cave 100 meters beneath the surface? I mean, just getting the pieces down there seems impossible.
Well, the solution was pure genius. They basically treated it like a set of gigantic, high-tech Lego blocks. Instead of trying to build it bit by bit way down in the cavern, the engineers designed the whole thing in 15 massive, complete slices. They built and tested each slice up on the surface, and then, very, very carefully, they lowered each one down into the cavern to be assembled. It was an incredible feat of engineering that saved a ton of time.
So we know it's huge. We know how they built it. But how does this giant mechanical eye actually work? The best way to think about it is like a giant cylindrical onion. We're going to peel back the layers one by one, starting right at the fiery collision point in the center and working our way out.
Right at the very core, where all the action happens, you've got the silicon tracker. You can think of this as the detector's inner eye. Its only job is to record the exact path of every charged particle that comes flying out of that collision. It catches the very first clues about what was just created.
And when you zoom way, way in, the technology is just beautiful. What you're seeing here are the silicon pixel sensors. These little guys are the building blocks that let the tracker pinpoint a particle's location with absolutely incredible accuracy.
Now this is where it gets kind of nuts. The tracker uses about 75 million of these individual sensors, all working in perfect harmony. Together, they create what is essentially a super detailed 3D digital photo of every single particle's journey.
All right, moving one layer out, we get to the electromagnetic calorimeter, or ESAL for short. Now, its job is totally different. Instead of just tracking where a particle goes, the ESAL is designed to stop certain particles, like electrons and photons, dead in their tracks. It completely absorbs them so it can get a perfect measurement of all their energy. And the material science here, it's just astonishing. The ECLS is built from almost 80,000 flawless lead tungstate crystals. And these are not just any crystals. To get them pure enough, each individual crystal had to be grown for 2 full days. Just doing the math on that is staggering. It was a decade-long project just to make the raw materials for this one layer.
Okay, the next major layer, the Hadron Calorimeter, has one of the coolest origin stories in all of science. It's this amazing blend of history and physics. By the way, a hadron is just a particle made of quarks, like the protons they're smashing together.
So, to build this component, the engineers needed a massive amount of really high-quality brass. And it turns out the perfect source was sitting in Russian military storage, thousands upon thousands of artillery shell casings from old warships. So, in this incredible symbolic gesture, these tools of destruction were melted down and reformed into an instrument of pure discovery. How cool is that?
Finally, we reach the very outer edges of our onion, the muon chambers. Now, muons are like the heavy, superpowered cousins of electrons. They're the escape artists of the particle world. Most particles get stopped by the inner layers, but muons can blast right through meters of dense material. They're the only things that are likely to make it all the way out here, so this whole system is built specifically to catch them.
And here's the clever way it works. As a muon zips through one of these long gas-filled tubes, it bumps into gas atoms and knocks some electrons loose. Those electrons then drift towards a wire in the center, creating a tiny little electrical pulse. It's like leaving an electronic breadcrumb. You connect the dots from all the breadcrumbs, and bam, you've tracked the muon's path.
Now, you build all this incredible hardware, you create this amazing mechanical eye, and in doing so, you create another problem. A problem on an almost unimaginable scale: data. The sheer amount of information this thing generates is just a torrent. Try to wrap your head around this number. Inside that detector, the beams of protons are smashing into each other 40 million times, every single second. And each one of those collisions sprays out a whole new shower of particles that the detector has to see and record. Obviously, there's no way to save all of that, so a super-fast automated system sifts through those 40 million events a second, trying to pick out the interesting ones. But even after throwing away 99.99% of everything, the detector still pumps out over 5 petabytes of data every year. That's 5 million gigabytes. It's an absolute flood.
So how do you handle a data deluge like that? No single supercomputer on the planet could do it. The solution was as ambitious as the detector itself. They basically built a global computer, the worldwide LHC computing grid. It links up tens of thousands of computers at labs and universities all over the planet, all of them sharing the load to process that fire hose of information.
And you know, that really brings us to what I think is the most important part of this whole story. Because beyond all the concrete, the steel, the silicon, and the petabytes of data, this is, at its heart, a human story.
Just the CMS experiment alone involves around 2,000 scientists and engineers. They come from over 240 institutions in more than 50 different countries. It's just a stunning example of what we can all achieve when we decide to work together to answer the biggest, most fundamental questions there are. These detectors aren't just marvels of engineering. They are monuments to our shared, unshakable curiosity about the universe.